So I will continue my lecture. So last time I said I would study today the large size limit, the maps of very large size, but I still have to do a few things before that. So remember, so we had this. So we want to count maps. Remember that TG L1 Ln is the sum of maps with marked faces of length L1 up to Ln on genus G. Okay, and we had, so now let me consider the case where we have one marked face on genus 1. Okay, so we have one marked face. And something like that, right? So let's try to continue to compute this. The other day I wrote Todd's equation. So let me remind. So TL was equal to sum of Tj TL plus j minus 2, j equals 3 to d, plus, so this is the case where on the other side of the marked edge we have an unmarked face, plus, and what happens if we have the same marked face on the other side, so either we disconnect, so sorry, this is in genus 1, plus, so we have the case where we get, so when we have the other marked face, so somehow we are on a torus, and imagine the marked face is here. When we cut this marked edge, we get something like that, which is a cylinder. So we have sum over L prime equals 0 to L minus 2 T 0 L prime L minus L prime minus 2 plus, and sorry, that's all. Yes. No, sorry. There is another possibility. It's where instead of this, you have, well, the handle is on one side. Okay. The handle is on one side, so then you get plus sum from L prime equals 0 to L minus 2 of T L prime 0 T 1 L minus L prime minus 2. It can be on one side or the other side, so which means you put a factor 2. So if you multiply this by 1 over x to the L 1 over x to the L, yes, and then sum over L, what you will get is the equation for the function which I called W1 1 of x. So v prime of x, and again, as usual, we have to take the negative part to take into account the terms which don't appear in the sum, equals, and here this is the function w, this is the function w02 of x plus, and here we have the function 0, 1 and 1, 1 to w 0, 1 of x, w1, 1 of x. So this is the equation. And this thing means that this is equal to w1, 1 of x, v prime of x, minus a certain polynomial of x. Which is just the sum over the L's, which are not into the sum. So basically the L, it contains sum from, I think, x to some powers, which go up to, I think, d minus 3 of degree d minus 3. Right, so this is the equation. Now we want to solve this equation. Last time I showed you what the value of W20 was, and W10 we already know it. Okay, so we know already W10 and W20, and now we want to compute W11. So, well, what we can write is W11 of x. Well, we have v prime minus 2W10. We'll put them in the denominator. W20 of xx plus p11 of x over v prime of x minus w10 of x. Sorry, 2w10 of x. This is just the same thing as above. Well, one of the problems is that we don't know p11 of x. One thing we know is that w10 of x was 1/2 of the prime of x minus square root of, I wrote it this way, x minus a, x minus b times some q of x. So you see the combination v prime minus 2w10 is this quantity. So v prime of x minus 2w10 of x equals 2 square root of x minus a, x minus b times q of x. So which means that w11 of x equals w20 of xx plus p11 of x over 2 square root of x minus a, x minus b times this q of x, right? Now we don't know what p11 is. And well, there is a technical lemma. So w11 of x, and in fact it's general, wng of x and other variables, has no pole at x equals 0 of q. And well, if you're careful enough, the degree of q is q minus 2. Here, in fact, the degree of q equals d minus 2. P11 is a polynomial of degree d minus 3, so it has d minus 2 unknown coefficients. Okay? So P11 has d minus 2 unknown coefficients. And we know that the numerator should vanish at exactly d minus 2 points. So we have exactly the same number of equations and unknowns. So we can determine P11. So I repeat. I will show where this lemma comes from in a minute. But let us assume that this lemma. So degree of P11 equals d minus 3, which you can, well, I mean, it's just, you can see it just by seeing what is, so v prime v prime behaves like x to the d minus 1 when x is large, because v prime was sum of tj x to the j minus 1 from j equals 2 to d. So it's a polynomial of degree d minus 1. W11 of x contains the sum over 1 over x to the L plus 1, where L is the length of the marked face, and the marked face has necessary at least length 1. Okay? So this means that it behaves like O of 1 over x squared. So the product, W11 times V prime, behaves like x to the d minus 3 at infinity. So this is why when you take the positive part, P11 is a polynomial of degree d minus 3. Okay? Now, the fact that Q has degree d minus 2, well, if you take the definition which I computed the other day, but an easy way to see it is that W10 should vanish at infinity. Again, for the same reason, because it starts with 1 over x to the L plus 1. It behaves like 1 over x to the L plus 1, so it should vanish at infinity. So it means that this term should behave like the same power of x as this term. And this one behaves like x to the d minus 1. And square root of x times x behaves like x, so Q must behave like x to the d minus 2 at infinity. Okay, so degree of Q equals d minus 2. So it has d minus 2 zeros. And P11 has d minus 2 coefficients, which for the moment we don't know. The lemma says that this quantity should not have poles at those d minus 2 points. So which means that the numerator must vanish at those d minus 2 points. So basically it means that we know the value of P11 at d minus 2 points, which should be minus the value of this at those d minus 2 points. And so we have a polynomial of degree d minus 3. We know its value at d minus 2 points, so we can determine it. Okay, so in principle, we can determine everything doing that, but I will show you a shortcut. In fact, we never have to determine this polynomial. It's too tedious. I mean, you apply Lagrange formula, interpolation formula for the polynomial. You can do that, but it's very tedious, and there is a shortcut. So let's see the shortcut. Well, just where this technical lemma comes from, it's because, well, it's basically because of that, because W11 of x is a series with poles only at 0. Well, okay, I don't want to enter the details, but it's a series with poles only at 0. And in fact, when I write t to the v, t3 to the n3, and so on, t4 to the n4, as a formal series in n3, n4, and so on, for each given power, let's say for each given power of t, the coefficient is in fact a polynomial in 1 over x. There is only finitely many maps with a given number of vertices. So, so it's a polynomial, and that's why it has poles only at 0, and it cannot have poles at other places. Okay. So now let me make an remark. Go to the z variable. So I remind you that we wrote x equals alpha plus gamma z plus 1 over z. And this variable is the variable which uniformizes everything. So in the z variable, everything becomes rational functions. So for instance, in this z variable, remember that W2 0 was 1 over well, of x1, x2 was 1 over z1 minus z2 to a square. In fact, you need to divide by x prime of z1, x prime of z2, minus 1 over x of z1 minus x of z2 to the square. Okay. And so, well, basically, when you go to the z variable, this term is a rational function of z. This term is a rational function of z. This term is a rational function of z. And since P11 is a polynomial, it is necessarily a rational function of z as well. So in this z variable, W11 is a rational function of z. So let me write it this way. So I won't need that anymore. So W11 of x of z, and I will also multiply by x prime of z, because I already explained W11 transforms like one form when you change variable, equals, let's define, so by definition, omega 11 of z. Right? So, and we know that this is a rational function of z. And we can even see where the poles are. Well, in this expression, this has a pole. I remind you that square root of x minus a, well, okay, square root x minus a, x minus b, it's easy to compute. It's gamma z minus 1 over z. It vanishes when z equals plus or minus 1. Okay? This quantity, the W20 at the same point, at z1 equals z2, you can check that also it vanishes at plus or minus 1. Well, W20 of x of z, and in fact you can even compute it. I think it's something like 1 over 4 gamma square z square minus 1 to a square, or something like that. Well, I'm not sure. Well, times some coefficient, which I don't remember. But what I want to say is that it also has poles only at z equals plus or minus 1. All right. P11 is a polynomial in x of z. So it can have poles possibly at z equals 0 and infinity, because x contains a 1 over z. So P11 of x of z could have poles at z equals 0. But if you look at the degrees, P11 divided by Q, Q has a degree which is larger than P11. And in fact, this means that there can be no pole. So omega 11 of z has poles at z equals plus 1, minus 1. At 0, it cannot have poles, just by looking at the degrees, the ratio of the two terms. So this one diverges with like z to the power, like 1 over z to the power d minus 3, and this one has 1 over z to the power d minus 2, so the ratio is not divergent at z equals 0. Same thing at infinity. When z goes to infinity, the ratio remains finite. There is no pole at infinity. And the only other possible poles would be the places where this vanishes. But from the lemma, we know that there is no such poles. So there is no other pole. only at those points. So, so it's a rational function, and we know where its poles are. Let's write Cauchy residue formula. So omega 1 of z equals residue when, let me call that z prime going to z, of 1 over z prime minus z, omega 1 of z prime. As I said, you should always see that as you should always view a residue as an integral, so never forget the integration variable, because you might have to do changes of variables. So it's just saying that the residue, well, I mean, taking the residue at the pole z prime equals z just picks the value at z prime equals z. So this is kind of obvious. But now we know that this is a rational function which has poles. So this product has poles at z prime equals z, and it also has poles at z prime equals plus or minus 1, and no other pole. So, and we know that for every rational function, the sum of residues of all poles must vanish. This is true in general for every rational function. So then this is minus the residue at z prime equals plus and minus 1 of the same expression. Okay. It seems obvious to say that. Okay, I will need this. Okay, this is really obvious to say that, but there is one good thing now. Omega 1 of z equals, so let me change this, let me put this minus here. Residue when z prime goes to plus or minus 1 of 1 over z minus z prime dz prime, and omega 1 of z prime. But now let's use this. Let's use the Tut's equation. So this was the Tut's equation. So let's replace this by that. Don't forget the x prime. So x prime of z prime times this quantity W20 of x of z prime plus P11 of x of z prime divided by this expression, which, if you remember, I said that this expression, I call it minus y of z. This is a definition. It's just to make it shorter. So this is minus y of z prime. Well, okay, let me put the minus again here. Okay. Minus y of z prime. So this is what we have. Now observe that this quantity vanishes at z prime equals plus or minus 1, because x prime of z prime equals gamma 1 minus 1 over z prime square. Just the derivative of z prime plus 1 over z prime. So this vanishes when z prime equals plus or minus 1. Y also vanishes when z prime equals plus or minus 1. So the ratio of these two things has no pole at z prime equals plus or minus 1. So x prime over z prime over y of z prime has no pole at z prime equals plus or minus 1. W20 has poles. W20 of x of z prime has poles at z prime equals plus or minus 1. And P11 of x of z prime, well, it's a polynomial, so it cannot have poles. So this means that P11 times x prime over y has no pole at z prime equals plus or minus 1. So it has no residue. So you can forget it in the formula. So you don't have to compute it. So what you get, the theorem, is that omega 1 of z equals minus residue when z prime equals plus or minus 1 of dz prime over z minus z prime, x prime of z prime, W20 of x of z prime over y of z prime. And now we know everything in the right-hand side. So it means we have recomputed this function. I mean, you can even, I mean, since this is an explicit quantity, you can really evaluate the residue. I will not write the formula because there are, I think there are, I was probably wrong. It was a higher power here. It's probably 4. Well, okay. You have to compute poles of order up to 4. So, I mean, just a sum of 4 terms, but it can be written completely explicitly. I will not do it here. What I just want to show is the structure of this, this expression. There is, let me put those terms together. And let's call that k of zz prime. So what we have is that omega 1 of z equals residue when z prime equals plus or minus 1 of k of z prime, and this quantity is, so this omega 20 of x of z prime, Well, there is a graphical representation of this. K of zz prime represented by an arrowed edge, zz prime. So let's say this is k of zz prime. And while W20 of x of z prime, let's represent it by an arrow with no edge, an edge with no arrow. And this product here means, and k somehow it has two, well, okay, it contains a, well, okay. So this formula just says that omega 1 is, well, okay. Don't know if it's so. You just take this at z prime equals z and glue it at this point. Okay, so it's just a graphical notation to represent this formula. So you see, it's in somehow what you get is a graph with one external leg. Each time you have a vertex means you are going to take an integral, which is in fact a residue at z prime equals plus or minus 1. And each time there is an edge with no arrow, it's a W20. And this is going to be general. So, general case. So define, so Wng of x of z1, x of zn, multiply by x prime of z1, x prime of zn, and call that omega ng of z1, zn. And the idea is that every omega ng will be given by a similar formula. You can prove by Todd's equation exactly doing the same steps I did here. And can be represented graphically. And so the general theorem is that So omega n plus 1g of z 0, z1, zn equals residue at the variable z prime equals plus or minus 1, k of z0, z prime times omega n plus 2 g minus 1 of z prime, z1, z2, and so on, zn, plus sum from h equals 0 to g, sum over I bar equals the variable z1, zn. And here in this sum you have omega 1 plus cardinal of I, h, z prime I, and omega g minus h, 1 plus cardinal of I bar, z prime I bar. It's more or less the same terms we had in Tutt's formula, in Tutt's equation, except that in Tutt's equation there was also a polynomial which has disappeared here by taking the residue because it gives no pole. And there was also another term with some derivatives with respect to the zi's, and for the same reason it also disappears because it gives no pole. So we get only this formula. And so this is called the topological recursion. You can check that, so if you write chi, well, minus chi equals 2g minus 2 plus n, okay? The value of chi, which appears in the left-hand side, is strictly larger than all the values of chi's which appear here, there, or there. Sorry, here, let me define a sum which I call sum prime, which means that exclude the terms. Well, basically, in the right-hand side here, you see you have some omegas with some index, upper and lower index, which appear. And in case there is a term which is basically the one you have in the left-hand side, you must exclude it from the sum because it is the one we put in the left-hand side somehow. So exclude the terms where you have w n plus 1g. In fact, there are only two possibilities to have wn plus 1g. It's when h equals g and I is the full set. So I bar is the empty set, or the contrary, h equals 0 and I bar is the full set, so I is the empty set. So there are just two terms which you must exclude in this sum. So the fact that chi decreases, minus chi is strictly larger in the left-hand side than in all terms in the right-hand side means that if you want to compute the left-hand side, in the right-hand side you have only, the right-hand side involves only functions which you have already computed at the previous step. So this is really a constructive recursion relation. I mean, from this recursion relation you can really compute everything. It really, this recursion computes everything. So it computes every omega ng. Sorry, with n larger than 1. Because we have this n plus 1. It does not compute the omega 0g. So just let's take an example. So in fact, omega 1,1, we have seen what it was. In omega 1,1, in fact, there is no term here. And we have only the omega 2,0 which appears. So omega 1,1 of z, 0, is residue of k z0 z prime, omega 2,0 of z prime, z prime. This is an example of this recursion. Another example would be omega 3, 0 of z0, z1, z2 would be a residue of k z0, z prime. And here we don't have this term because this term appears only if g larger than 1. And we have here, we want to split z1, z2 into all possible subsets in all possible ways, and we must exclude those terms. So there are only two possibilities. There is omega 2, 0 of z prime, z1, omega 2, 0 of z prime, z2, plus omega 2, 0 of z prime, z2, omega 2, 0 of z prime, z1, which is in fact the same term. So I could have put a factor of 2. Diagrammatically, this would be represented as this times this times this. K times omega 2, 0 and omega 2, 0. Okay. And you can go on. Now, I also did not say how to compute. Sorry, to compute. So what I called FG, which was the W0G, which is also the same thing as what I will call omega 0G. So how to compute that? Because in this recursion, we need to have always at least one variable, so at least one marked face. In Tut's recursion, you need at least one marked face. So, but remember that we had the relationship that dfg over dtk must be equal to, so k dfg over dtk must be equal to the residue of omega 1g of x to the k dx when x goes to infinity, which is the same thing as residue when z goes to infinity of omega 1g of z, x of z to the k dz. So now we have a recipe to compute omega 1g. So we have, let's say we have computed omega 1g, and so the trick is to find some value fg whose derivative is that with respect to every tk. And well, somehow you have to compute the integral with respect to tk. That may look not so easy. And the idea is to guess a good expression and check that it satisfies the good derivatives. And then the good guess are the following. So f1 equals 1 over 24. This is the same 24 there was in the lecture, in the previous lecture about conformal field theory. I mean, it comes for the same reason. Log of gamma square, y prime of 1, y prime of minus 1, and divided by t. And for g larger than 2, fg equals 1 over 2 minus 2g, residue when z goes to plus or minus 1 of omega 1g of z times phi of z. And where phi of z, phi prime of z is y of z, x prime of z. And remember that y of z was the square root. So y of z was the square root, so minus square root of, so square root of x of z minus a, x of z minus b, times q of x of z. So you take this formula, and that allows to compute every fg, f1, and I wrote the expression of f0 the other day. So that really allows to compute everything. In fact, the other day I said that this curve, so if you plot x and w10 of x, so it's a certain curve in the complex plane. Well, okay. Sorry, it should be represented. So well, okay. Let me write it more like. So if you plot only the real part, it looks like that. But you should think that somehow this is a certain Riemann surface embedded into C cross C. C cross C. This is a certain Riemann surface. And this curve is naturally equipped with a certain Laplacian related to this function phi. There is a metric on this curve related to this phi. I don't want to enter the details. So there is a certain Laplacian on it. And this quantity, it turns out that this is 1/2 log of the determinant of this Laplacian. So just to say that those fg's, so f0, I said the other day, is also a special invariant of that curve called the prepotential. f1 is related to the log of the determinant of the Laplacian, and every fg is somehow an invariant of that curve, a geometric invariant of that curve. So I will not enter the details, but basically, once you know the curve, once you know this Riemann surface, all those generating functions are some invariants of that Riemann surface and can be computed just by the geometry of that Riemann surface. So you can somehow forget about the combinatorial problem of counting maps and just give yourself a certain Riemann surface and compute its invariants. And, okay. Now I can go to the large size limits. Well, what happens, so large size. I should change the pen. So the question is, how do those generating functions behave when we want to count? So remember, let's say, for instance, f0, well, let's say fg, was the sum over all maps of genus G. And here I put no marked face, so I have to divide by the number of automorphisms. And let's say t to the number of vertices, and let's say t, for instance, for quadrangulations, t4 to the number of quadrangles. So if we want to know how many maps have exactly n4 quadrangles, we need to take. Let me choose also t equals 1. In fact, for quadrangulations, there is a relationship between the number of vertices and the number of quadrangles. So in fact, it's redundant. So let me take this simple example. So, and so this is sum of, let's say, C n t4 to the n. 1. And so C4, this is exactly the number of maps with n4 quadrangles. Well, it's the number up to automorphisms. I mean, it's the number divided by automorphisms, but it's really a good way to count maps. It's really the way you want to count maps. So, question. Asymptotic. Or let me put also an index G of C and 4G when n4 goes to infinity. Sorry? Okay. So, so we want to know how the coefficient of a series behave at large orders. And there is a general method, I mean, now some generalities about large order behavior of a series. So let's say, let's consider a series A of x equals sum of an x to the n. Well, so the example, let's take a basic example. A of x is, well, you see, if A of x, typically we choose a polynomial, or also if we choose a rational function, the large order behavior will not be very interesting. So we better choose a function which has some singularities. I mean, otherwise the large order behavior is kind of trivial. So the simplest example is 1 minus x, let's say, divided by xc to some power alpha. So this is the generic example. Then we can expand that. Sorry, let's put let's put a minus. So this is sum over k of so the binomial alpha k minus 1 to the k x to the k. Xc to the minus k x to the k. So somehow this is the coefficient ak. And it's easy to see how it behaves at large k. You use Stirling's approximation formula for the binomial coefficient. And at large k, ak behaves like, so xc to the minus, so minus xc to the power k times, so the asymptotic of alpha of this coefficient alpha k is k to the alpha, I think. Is that right? Sorry? Yes, minus k. Yes, I think it's k to the alpha. While times some constant, which depends on alpha. So you see that typically when there is a singularity of type, when there is an algebraic singularity, it will behave like a power law. The large order behavior behaves like a power law. And this is kind of generic. So so in general, large order behavior is completely equivalent to the study of singularities. There is a full theory about that by, for instance, Borel transform or things like that. So, but somehow knowing the singularities of a series is equivalent to knowing its large order behavior. So, which means that here we have this FG, and instead of really studying the large order behavior, I will study the singularities. But it's completely equivalent. Knowing one, you know the other. There is general formula for that. And in fact, in statistical physics, most people prefer to study the singularities of a series, of a generating series, rather than the large order behavior directly. So in our case, let me give you some examples. Well, examples. So let's see our F1 for quadrangulation. So quadrangulations. Remember that in our quadrangulations problem there was this gamma square which was 1/64 1 minus square root of 1 minus 12 tt4. And here I've chosen t equals 1. Well, first, you can already guess that something special will happen when t4 equals 1/12. You can guess that that's where the singularity is going to be. And indeed, that's what happens. So if you take the general expression I wrote for F1 just before, you can check that in this case, just apply the general formula, is log of 2/1 plus square root of 1 minus 12 t4. Probably there is a minus 1. Sorry. Yes, no, sorry. Okay. So this is an example. This is the value of F1. And you see that indeed it is singular at, no, sorry, 2R. So, yes, there is a minus. Sorry. So, this is singular. At t4 equals 1/12. And the singularity is logarithmic. In fact, a more interesting quantity is the second derivative of f1 over dt4. This one will behave like 1/1 minus 12 tt4 to the power 2. Well, there is a coefficient here. But the important thing is the exponent minus 2. And in fact, we want to know the coefficient. It's 1/48. And this is also an important coefficient. Well, you can play the same game with the other. Well, if you compute the first few fg's. So, for instance, let me give you the d2 f0 over dt4 behaves like minus 1/2 of 1 minus 12 tt4, sorry, to the power 1/2.
Is the second derivative?
Sorry, second derivative. d2 f2 over dt4 square behaves like 49 over 3 to the 2 times 2 to the 8. Sorry, here I had this 1/12 to the square, and here 1/12 to the square. 1 minus 12 tt4 to the minus 9/2. So you can compute the first few of them, and things which are important are the exponents, but also the prefactors. Well, in fact, let me forget about the power of 1 over 12. So, in fact, and in general, in general, we find so d2fg over dt4 to the square will behave like a certain coefficient, let me call that f tilde g, times so 1 over 12, which is the critical value, to the power 2 minus 2g, times 1 minus 12t4 to the power to the power no, sorry. Let me not take the derivative directly. Fg to the power 2 minus 2g times 5, 4. And so the second derivative, it's a certain coefficient. So, and in fact, the problem is indeed to determine this f tilde g. And so it means that dfg, d2fg over dt square will behave like a certain coefficient which I'm going to call ug. So 1 over 12 to 2 minus 2g. There will be the 12 to the square coming. 12t4 to the power 2 minus 2g 5 over 4 minus 2. Okay. And well, the relationship between ug and f tilde g is very simple. There is this taking the first derivative brings this 2 minus 2g times 5, 4 and 2 minus 2g times 5, 4 minus 1. I mean, it's okay, just I prefer. In fact, this is a more interesting coefficient. This is the one I wrote here. You see? Well, sorry. Let me not put this one. Okay. This is the coefficient ug I wrote here. So question is how to determine, so question, what is ug? Well, in fact, even before that, there is an important remark. It's this exponent. This exponent, it's not something arbitrary. It's something which is related to the KPZ formula. It's an exponent of the KPZ formula. For the minimal model, (3,2), which has central charge c equals 0, and which is called pure gravity. In fact, this is the 5, 4, which is rated. And so in general, for a PQ minimal model, the KPZ would give that this, what replaces this 5, 4 would be P plus Q over P plus Q minus 1. And so in our case, this is 5 over 4. Because this is the 3-2 minimal model. So why does this have to do with KPZ? Well, what is expected is that if you take, the limit of large maps should be somehow a random surface, and with a random metric on it, And it is expected that this is related to Liouville theory, exactly what was explained in the previous lecture. So what is expected, expected large maps should be Liouville theory. Liouville conformal field theory. And so, when you study just large maps, so with nothing, not with an Ising model, nothing on it, you expect indeed to find somehow pure gravity. So Liouville with nothing else. If you start studying large maps corresponding, for instance, to an Ising model, you would expect another minimal model. So, for instance, the Ising model would be 4-3. And then this P plus Q over P plus Q minus 1, you can compute what it is. And in general, the central charge for the PQ minimal model is 1 minus 6 P minus Q to the square over PQ. And you can check that for 3-2, this is 0. And for the Ising model, this is 1/2, which is related to the spin 1/2 field. So, example, Ising model should correspond to the 4-3 minimal model, which has central charge. You can check 1 over 12 multiplied by 6, that's 1/2. 1 minus 1/2, it's 1/2. And the P plus Q over P plus Q minus 1 would be 7 over 6. Well, the Potts model, I think the Potts model with 3 states is also expected to be a conformal field theory, I think, with 5-6. Well, sorry, 5-6? No, I think. But this has never been, I mean, even physicists are not sure about. So, well, okay, so this is what you expect. And one thing is that Liouville conformal field theory, so prediction from KPZ. So it predicts that this exponent, KPZ formula predicts the exponent and also predicts the prefactor. So what we want to check is whether the prefactor matches with KPZ. Exponent. So the exponent will be 2 minus 2g P plus Q over P plus Q minus 1. And prefactor. UG. So the same UG here. And for pure gravity, so KPZ implies, well, in fact, it's not really the same paper of KPZ. In fact, it's a work of, I think it's in a work of Belavin, probably the BPZ paper predicts this number. But basically, it says that if you make a generating series out of those UGs, so define U of S equals sum over G of UG S 1/2 minus G minus, minus 1 minus 5G over 2, sorry. So sum over G UG S to the 1 minus 5G over 2. Okay, should satisfy the Painlevé-1 equation. So which is 3u squared plus u second equals S. So this determines all the coefficients UG by recursion. I mean, if you plug this expression into that, you can determine all the UGs. And so this is a prediction of conformal field theory. Well, I mean, I should not call it KPZ, but more conformal field theory. Knižník, yeah. Well, KPZ is really the prediction for the exponent, but in fact, I'm not sure in which paper this was first done, but well, okay. It's the well. Okay, minimal models basically in conformal field theory satisfy lots of differential equations, and this is one of them. So question is, can we prove that limits of large maps do satisfy that? And the answer is yes. In fact, we can prove it. And the reason is we have this very explicit expression for FG with this residue formula. And the nice thing is that this topological recursion, it goes to the limit very easily. It's very easy to take the limit when T4 is close to 1/12. In fact, taking the limit commutes with the topological recursion. Well, topological recursion commutes with limits, so it's very easy to compute limits to all orders, and it's easy to check. Well, I should not say it's easy, but it's possible to prove this. So, sorry? Well, in fact, it was first done in a very heuristic way by Kazakov in the late 80s, early 90s. So the theorem. So the UGs coming from large maps are equal to the UG from CFT. And well, here I wrote the coefficient corresponding to the limit of Fg, which is the generic functions of maps with no marked face, but there are similar conjectures from conformal theory for all the other WNGs, and the scalings on their coefficients, and all of them match. So that does not prove that large maps are Liouville theory, but it just gives some checks. I mean, we just prove some parts of a general conjecture. For instance, we cannot say everything about expectation values of points on at given places on the maps. I mean, well, so this was done heuristically. I think it was Kazakov. I don't remember. It was the late 80s and 90s. In fact, Kazakov was deriving that from matrix model. At the same time, KPZ were working on the conformal field theory, and somehow KPZ wanted to check their prediction on some example. And they wanted to check that on the Ising model, which Kazakov was solving from matrix models. And so Kazakov computed the critical points, so the singularities of the Ising model. And
matrix models, do you mean the random matrix?
Yes, random. Yes, but which is the same thing as stat equations, in fact. But Kazakov found the exponents for the singularities of the Ising model, for a singularity of the Ising model, and it did not match the KPZ formula. So KPZ were very hesitating before really publishing the result, but I was told this story. And in fact, it's because Kazakov took the wrong singular point. In fact, there are two singular points in the Ising model. There are two singularities, and he started by looking at the wrong one. Which is the 5-2 minimal model. And later, it was realized by a student that there is another singular point, which is indeed the 4-3 minimal model. So KPZ works. So Kazakov did that by taking some asymptotic expansion derived from doing some saddle point methods on random matrices, which are not justified. There is no rigorous proof of those saddle point methods for large random matrices. And more recently, it was proved. It was reproved rigorously by using my method. So, but well, okay. But it was known for a long time. So this is the end of my lecture. So it was just to give an overview of what you can do. It's basically to show that in those random maps, we can really compute everything. All those generating functions can be computed exactly. We cannot compute everything, but we can compute all those generating functions. And we can even study the large order behavior limits. So we can recover the predictions of conformal field theory. And this can be done for maps with an Ising model, for maps with an ON model, for various sorts of maps. Okay, thank you for your attention.